Hi guys, I'll be presenting our project titled An Experimental Study on Cultivation and Growth Performance of Pleurotus sp. Mushroom cultivation is increasingly recognized as a sustainable agricultural practice. It converts agricultural waste into nutritious food, supports small-scale economies, and promotes environmental resilience. Our study focused on viability of cultivating Pleurotus species mushrooms under controlled conditions using locally prepared substrates, and the motivation behind this project is to explore affordable and renewable food production systems, particularly those that can be integrated with clean energy sources such as solar power. Next, the expected outcome of this project is a comprehensive evaluation of Pleurotus growth performance. We aim to identify key developmental stages, determine the timeframes for pinhead emergence and harvesting, and assess the impact of contamination on yield. It is anticipated that Pleurotus mushroom cultivated on enriched sawdust substrates under controlled humidity and temperature will show consistent growth, minimal contamination, and efficient fruiting body development. This will validate the effectiveness of our cultivation technique and demonstrate its relevance to sustainable agricultural practices. For instance, previous research provides a strong foundation for our work. First, Chang and Miles 2004 emphasized that lignocellulosic substrates such as sawdust and rice straw are ideal for Pleurotus growth and supplementation with rice bran enhanced yield. Second, Roise, Bars, and Tan 2017 highlighted that adding minerals like dolomite improves substrate quality and supports fruiting body development. Third, Jamil et al. 2019 report that enriched substrates produce higher biological efficiency compared to non-supplemented ones. And the last one, Agajani et al. 2018 found that environmental control, especially humidity and temperature, is critical for minimizing contamination and optimizing growth. Together, these studies validate our chosen methodology of using sawdust enriched with rice bran and dolomite under controlled incubation conditions.
Under the project planning phase, this project requires several important resources to ensure the successful cultivation of mushroom. These resources are divided into biological resources and equipment. For biological resources, mushroom spawn is used as the main source of fungal growth, sawdust serves as the primary growing substrate, providing structural support and nutrient. Rice bran is added as a supplementary nutrient to enhance mycelial growth, while dolomite is included to adjust and stabilize the pH level of the substrate. In terms of equipment, polybags are used to contain the substrate mixture during cultivation. A shovel is needed to mix the material evenly, while a weighing scale ensures accurate measurement of all components. Water is required to maintain adequate moisture content, and rubber bands are used to secure the polybag during preparation. For the treatment block methodology, the first phase involves substrate preparation. Initially, sawdust was soaked in clean water overnight to ensure sufficient moisture absorption. After soaking, the sawdust was transferred into a perforated plastic basket. It was then manually pressed to remove excess water, preventing overly wet substrate condition. Next, the prepared sawdust was thoroughly mixed with 650 grams of rice bran and 150 grams of dolomite. Rice bran was added to enhance nutrient content, while dolomite was included to help stabilize the pH level of the substrate, creating optimal condition for mushroom growth. In the second phase of the treatment block methodology, the prepared substrate was filled into polybags up to 3/4 of their capacity. This allows sufficient space for proper aeration and mycelial expansions. After filling, excess water was squeezed out from the polybags to prevent overly moist conditions that could affect mushroom growth. Finally, each polybag was weighed using a weighing scale to ensure consistency and uniformity across all treatment samples. Lastly, inoculation and cultivation were carried out. Mushroom spawn was placed on top of the prepared substrate to initiate mycelial growth. The polybag were then sealed using rubber band or a stapler to prevent contamination. After sealing, the polybag were kept at room temperature in an environment with high humidity and low light, which are optimal conditions for mushroom cultivation. Regular observation were conducted weekly to monitor the growth and development of the mycelium. For the commercial block methodology, an almost fully colonized commercial mushroom block was first obtained. The plastic polybag was partially opened at the top to allow access to the substrate. Any old mushroom spawn present on the surface was carefully removed to reduce the risk of contamination and to promote healthy new growth. After cleaning, the polybag was sealed again to prepare the block for further cultivation steps. Next, a moist tissue was placed on top of the mushroom block to maintain a high humidity environment. Edge-shaped cuts were made on the plastic surface to allow mushroom fruiting to occur. The polybag was then wrapped with a damp cloth and kept at room temperature to provide suitable growth conditions. Moist tissue and damp cloth were placed daily, and regular observation were conducted to monitor moisture level and the formation of mushroom pinhead. For the project roles, in week 1, all group members attended a lecture briefing on the mushroom cultivation project to understand the objective and procedure. During this week, a commercial mushroom block was received and designated as the control. At the same time, all members worked together to prepare the substrate for the treatment block, marking the beginning of the experimental setup. In week 2, all group members have each treatment block and control block per person. All group members were involved in monitoring both the treatment and commercial blocks. For the treatment blocks, observation of mycelium growth were initiated. Meanwhile, for the commercial block, the condition of the block was maintained and mycelium colonization was closely monitored to ensure healthy growth. In week 3, all members continued observing both blocks. For the treatment block, mycelium growth was monitored and weekly photographs were taken for data recording purpose. For the commercial block, all mushroom spawn was removed, and the block was covered with wet tissue and a damp cloth to maintain suitable moisture and humidity conditions. In group 4, all group members continue managing both experimental blocks. For the treatment blocks, the progression of mycelium growth was recorded, including any signs of contamination. For the commercial block, humidity level were consistently maintained and observations were carried out to identify the formation of mushroom pinhead. In week 5, monitoring activities were continued by all members. For the treatment block, mycelium growth was further observed and the percentage of substrate colonization was recorded. For the commercial blocks, blood condition and humidity were maintained and the preparation were made for the fruiting stage of mushroom growth. In week 6, all members continue observing both blocks. For the treatment blocks, mycelium growth was monitored and weekly photographs were taken for data recording. For the commercial blocks, humidity maintenance was continued and the growth of pinhead was observed. The time of pinhead appearance was also recorded for analysis. In week 7, all group members focused on data collection for both blocks. For the treatment block, measurement of mycelium running were taken and any sign of contamination were carefully documented. For the commercial block, the number of fruiting bodies was counted and their height and weight were measured to assess growth performance. In week 8, monitoring activities were continued by all members. For the treatment block, mycelium running was observed to track further progression. For the commercial block, blood conditions were maintained and humidity level were continuously monitored to support ongoing mushroom development. In the final week, week 9, all members carried out concluding observation and data recording. For the treatment block, final measurement of mycelium running were taken, photographs were captured for documentation and any contamination or growth failure was recorded. For the commercial block, a final harvest was conducted for any fully developed fruiting bodies.
I will now explain the scheduled monitoring implemented throughout the 9-week mushroom cultivation process. This includes monitoring growth stages from mycelium development until final harvest. During week 1, the project began with a briefing and design phase, where the objective methodology and the overall 9-week monitoring plan were introduced. In week 2, monitoring started by maintaining the mushroom block condition. The focus was on ensuring optimal substrate moisture and observing the initial mycelium colonization to confirm healthy early growth. In week 3, fruiting initiation began. High humidity was maintained while early pinhead formation was documented, and weekly photographs were taken for data recording. By week 4, visible pinning occurred. Monitoring focused on pinhead progression, maintaining humidity between 80 to 95%, and checking for any signs of contamination. During week 5, growth quantification was carried out by tracking the colonization percentage and monitoring overall block health in preparation for fruiting growth. In week 6, the reproductive timeline was monitored by recording the timing of pinhead appearance, observing mycelium running, and maintaining proper airflow and humidity. In week 7, quantitative assessment was conducted by counting the number of fruiting bodies and measuring mushroom height and weight. In week 8, succession monitoring focused on maintaining block conditions, supporting ongoing fruiting cycles, and continuing to monitor colonization progress. Finally, in week 9, the project concluded with final harvesting and evaluation. Final measurements were taken, total yield was recorded, growth success or failure was documented, and the incubation area was cleared.
Let's begin with the fruiting bodies count during the first growth cycle of the commercial blocks. Block B produced the highest number of fruiting bodies with a total of 18. Block A followed with 8, while Block C had the lowest count at 6. The difference here is explained by environmental placement. Block B was positioned in a favorable environment with higher humidity, which encouraged earlier pinhead formation and faster fruiting. In contrast, Block A and C were initially placed in less suitable condition, which is areas with lower humidity and poor airflow. This unfavorable placement delayed pinhead formation even though the mycelium had already colonized the substrate. Now looking at the mushroom weight harvested during the first growth cycle. Clearly, Block B outperformed the others, yielding 300 grams. Block A produced 180 grams, while Block C yielded 170 grams. The heavier yield from Block B reflects not only its higher fruiting body count, but also the fact that its mushroom had more time to develop under favorable conditions. Meanwhile, the delayed fruiting in Blocks A and C resulted in smaller and lighter mushrooms, reducing their overall yield. This demonstrates that early placement in suitable conditions directly impacts both the number of mushrooms and their final weight. In the second growth cycle, the performance shifted. Block A produced 6 fruiting bodies, while Block C yielded 4. Block B, however, failed to produce any fruiting bodies. The absence of growth in Block B was due to substrate desiccation. Its placement near a window exposed it to sunlight and low humidity, and poor maintenance, such as not replacing the damp towel used to retain the moisture, caused the block to dry out. Looking at the mushroom weight from the second growth cycle, Block A yielded 140 grams, while Block C produced 90 grams. Block B recorded 0 yield. Although the overall weights were lower compared to the first cycle, which is expected in subsequent flushes, the complete absence of yield in Block B emphasized the importance of consistent moisture management. This demonstrates that environmental neglect can erase productivity entirely, even in previously successful blocks. Turning to the treatment blocks, we monitored mycelial colonization over 9 weeks. Block B showed the best performance, reaching 90% colonization. Block C displayed delayed growth, reaching 40%. Block A had minimal growth, only 10%. Despite Block B's relatively strong colonization, none of the treatment blocks formed pinheads or mushroom. This indicates that full colonization, that is essential for fruiting, was not achieved. The uneven growth patterns suggest issues with substrate preparation, moisture content, or incubation conditions. Without complete colonization, fruiting cannot occur. Contaminant was a major limiting factor in the treatment blocks. We observed green fungal patches, reddish bacterial spots, and blackened substrate areas. These contaminants compete with Pleurotus species for nutrients and disrupted the substrate environment. Excess moisture, likely due to incomplete draining after soaking, create unfavorable conditions that promoted contaminant growth. This slowed mycelial expansion and prevented the blocks from reaching the fruiting stage. As a result, no mushroom yield was recorded from the treatment blocks. This highlights the importance of strict hygiene, proper substrate preparation, and moisture control during spawning and incubation.
In conclusion, oyster mushroom cultivation was successfully conducted, with harvesting achieved within 4 to 6 weeks, demonstrating that it is a far simpler and sustainable agricultural practice. Pleurotus species can be grown using agricultural waste with minimal technical skill, making this method environmentally friendly and accessible. However, proper control of temperature, humidity, moisture, and hygiene is essential for optimal growth. Differences observed between treatment and commercial block show that cultivation conditions significantly influence mushroom yield and quality. Contamination occurs due to excess moisture, poor substrate preparation, and inadequate cleanliness, leading to fungal bacterial growth that restricted mycelial development. Overall, this project is suitable for both educational purpose and small-scale commercial production. It provided valuable hand-on experience in sustainable agriculture, highlighted the importance of contamination control, and demonstrate the economic potential of oyster mushroom farming.